And welcome back. As we continue our cosmic journey through the solar system, let's go ahead and take a look at the origin of the solar system to really kind of get an idea of how things came to be. So we want to take a look at how the solar system formed. We first need to understand that much of astronomy is ultimately motivated by a desire to understand the origin of things. Each planet and moon is a very fascinating place that may stimulate our imagination as we try to picture what would it be like to visit there. So taken together, the members of the solar system preserve patterns that actually can tell us about the formation of the entire solar system. So as we begin our exploration of the various planets, we actually want to introduce our modern picture to how we believe that the solar system was formed based on the evidence that we have. So let's start by looking for patterns. One way to approach our question of origin for our solar system is to look for regularities among the planets. For example, we found that all the planets lie in nearly the same plane and revolve in the same direction around the sun. Well, that is a pattern, right? So that might tell us, could there be something here? Another pattern we notice is that the sun also spins in that same direction about its axis. So the planets are all spinning in the same direction as the sun is turning on its axis. Now astronomers say, hey, this pattern is interesting. How can we interpret this? Well, we interpret it as evidence that the sun and planets around it form together from a spinning cloud of gas and dust that we call the solar nebula. Additionally, we can do some spectroscopic analysis. The composition of our planets actually gives us another clue about origins. Spectroscopic analysis allows us to determine which elements are present in the sun and in the planets. The sun has the same hydrogen composition as Jupiter and Saturn, and therefore appears to have formed from the same reservoir material. In comparison, the terrestrial planets and our moon are relatively deficient in light gases and the various ices that form from the common elements, oxygen, carbon, and nitrogen. Instead, on Earth and its neighbors, we see mostly the rarer, heavy elements such as iron and silicon. So what's the pattern here? Well, this pattern is actually suggesting to us that the process that led to planet formation in the inner solar system must somehow have excluded much of the lighter material that are common elsewhere. Well, the most simple reason for this has to be the heat of the sun. The inner planets and most of the asteroids are made of rock and metal, which can survive heat, but they contain very little ice or gas which evaporate when temperatures are high. In the outer solar system, where it has always been much cooler, the planets and their moons, as well as icy dwarf planets and comets, are comprised mostly of ice and gas. So let's look at this also from the evidence far away, because of course, not like we have a time machine, we can go back and look at the birth of our solar system. But another approach we can use to help understand the origin of our own solar system is to look for evidence in other systems of planets that are forming elsewhere. As I mentioned, we can't go back in time to the formation of our own system, but there are many stars in space that are much younger than the sun that might be undergoing their own journey. In these systems, the processes of planet formation might still be accessible to direct observation. And we can observe that there are other solar nebulas, or flattened, spinning clouds of gas and dust surrounding young stars. And if we really want to apply that, we can say that these disks are actually resembling our own solar system's initial stages of formation billions of years ago. So when we look at these various different depictions, of course, we see what we would expect to see in our own solar system, just at a different star. So what about the planets themselves? How did they come about being built? So we got a kind of idea. So the sun had all this gas, it spun together, had this solar nebula, but where did the planets come from? Good question. Well, circumstellar disks are a common occurrence around very young stars, suggesting that the disk and stars form together. Astronomers can then use these different models to show that material begins to coalesce first by forming smaller objects, precursors of the planets, which we refer to as planetesimals. So you can think of this, decimal meaning, of course, small here. This process, though, is a very violent one, with the planetesimals crashing into each other and sometimes even disrupting the growing planets themselves. So you could have a planet that's forming, and here comes a friend, smashes into it, and now it's broken into pieces, and the process has to start all over. Now, because of these violent impacts and the heat from radioactive elements in them, all the planets were at one point heated until they were liquids and gases, and therefore differentiated, which also helps explain their present internal structures. Now, these complex collisions, of course, are a driving thing in the formation of our solar system. The process of impacts and collisions was not only complex, but it was also random. The solar nebula model that we assume our solar system formed under can explain many of the regularities that we find in the solar system. But the random collisions of massive collections of planetesimals might be the reason for the exceptions to some of the rules of the solar system's behavior. For example, we might say, like, why do the planets Uranus and the dwarf planet Pluto spin on their sides? Why does Venus spin slowly and in the opposite direction from the other planets? Why does the composition of the moon resemble Earth in many ways and yet exhibit substantial differences? These are all good questions. But again, the answers to these questions probably lie in the enormous collisions that took place in the solar system long before life on Earth actually began.